Good evening students. So those who have not subscribed my channel, please subscribe my channel and also share my videos. So let us start with another topic of electrical engineering, which is the phasor diagrams. So we will be starting with the phasor diagrams for the inductive load. Okay. So actually what are phasor diagrams? We should understand first what are phasor diagrams and how they are drawn. Okay. So phasor diagram are diagrams representing the alternating currents and voltages of same frequency as vectors or phasors with a phase angle between them. Okay. So they are the diagrams representing the currents and voltages by means of vectors or phasors. So when we represent the currents and voltages by means of some vectors, by means of some phasors, then they form phasor diagram. Okay. Phasors are arrows rotating in the anti-clockwise direction. Okay. So they are the vectors, but they are representing the scalar quantities. So here also we see that the scalar quantities are being represented by phasor diagram. Okay. By vectors, and that forms the phasor diagram of a transformer for the lagging load. For the lagging load, that means the load is inductive. So we have already seen how the transformer equivalent circuit looks like. Okay. So here the transformer circuit, equivalent circuit is being shown over here. The quantities which have to be represented in the phasor diagram are V1, which is the voltage source. Then it is connected with the R1 and X1. R1 is the primary resistance and X1 is the primary reactance, and they form primary impedance Z1. Okay, then the current starts flowing, the primary current starts flowing, and this is the no load current shown over here. This I1 and I0 also has to be shown on the phasor diagram. All the quantities these have to be shown on the phasor diagram. Okay, so this is the current IC or the working component of the no load current or the core loss component, and this is the magnetizing component, and this is the magnetizing component. Okay, so then it is this current is the I2 dash. I2 dash is the current which was responsible for nullifying the effect of the flux created by the secondary current. Okay, then this is the EMF, induced EMF E1 at the primary side. This is the induced EMF E2 at the secondary side. Then the secondary side is connected with the resistance R2 with the reactance X2, and they both are forming the impedance Z2, which is shown over here. Then the current starts flowing as soon as the induced EMF is set up. The current starts flowing in the secondary circuit, and the terminal voltage is being set up in the secondary side, at the secondary side. Okay. So these are all the quantities that has to be shown on the phasor diagram. So today we will be discussing here the phasor diagram for the lagging load. So we already know that if the load is resistive, then the voltages and currents are in phase with each other. But if the load is lagging, if the load is inductive load, okay, then the current will lag the voltage by 90 degrees. Okay, and it can lag by some phase, by some angle of phi also, by some any other angle also other than 90. Okay, and if the load is capacitive, the current leads the voltage either by 90 degrees, or it can lead by some angle phi, theta, alpha, whatever you are taking. Okay, so let us see the KVL, how the KVL equation looks like in this circuit. We have to apply the KVL and KCL equations in this circuit, and those equations we will be using for drawing our phasor diagrams. So let us start applying the KVL, Kirchhoff's voltage law, which you all have already studied in class 12. So let us start writing the equation for the KVL at the primary side first, and then at the secondary side. So at the primary side we are starting with okay. So at the primary side we are starting with V1. So V1 is there. it is a voltage source, then there will be drop in the resistance and the reactance, and the drop is always denoted by the negative sign. It's always represented by the negative sign. Since it is Kirchhoff's voltage law, so we will give the drop across it, the voltage across the resistance is given by minus I1 R1, okay, and the drop across the reactance is given by I1 X1, okay. Since it is a vector quantity, so you can also write here J, okay. And then the circuit is being completed, induced EMF is set up, so minus E1 is equal to 0. So this is the Kirchhoff's, we have applied the Kirchhoff's voltage law, KVL across the primary circuit, and we have got this equation. Now we see over here that the terminal voltage is greater than E1, induced EMF E1. Terminal voltage is greater than the induced EMF E1. So let us note down this point over here. Okay, so now let us start applying the KVL at the secondary side. So at secondary, okay, at the secondary side. So at the secondary side we will be starting from here. So it is E2 over here, minus, then the voltage drop across this resistance and the voltage drop across this reactance, okay. So minus I2 R2 minus J I2 X2, okay, and the terminal voltage which is being set up over here, minus V2 is equal to 0. So here we see that E2 is greater than V2. E2 is greater than V2. Okay. So here we see that my induced EMF at the secondary is greater than the terminal voltage V2. Okay. So these are the two equations which are very much important for drawing the phasor diagrams. Okay. So they are derived from KVL. Okay. Now KCL. Let us apply the KCL. We already know that the primary current is composed of two currents, that is the no load current and the load component of the primary current. Load component of the primary current is the I2 dash and the no load current is the I0. So the I2 dash is responsible for nullifying the effect of the flux which was set up by the secondary current, okay, and that flux was weakening the main flux. We have already seen all these factors in the working of a transformer, okay. So applying the KCL over here, we will be getting over here I1 is equal to I0 plus I2 dash, okay, at this point. And the no load current, we already know it is divided into two components. One is the working component and other is the magnetizing component. The magnetizing component is given by I mu and the working component is given by IC or IW. IC working component is also known as the core loss component, okay. So I0 is equal to I mu plus IC, okay, I mu plus IC. So these are the equations which we will be applying in a phasor diagram. So let us start quickly drawing our phasor diagram for the lagging load. So we have taken here the load to be lagging, that means the load is inductive. In the inductive cases, everywhere the current will lag the voltage by 90 degrees, either by 90 degrees or by some angle, by some phase angle, because the phasor diagrams are the diagrams representing the current and voltages of the same frequency as vectors or phasors with phase angle, okay. So let us start drawing. So we will be taking the flux phi as a reference. Now the students ask why we are taking the flux to be a reference, because flux is the only quantity which is linking the primary and secondary, That's why we are taking the flux to be our reference over here, Okay, then we will be drawing the induced EMF E1 and E2. Now the magnitude of E1 and E2 depends what type of transformer we have taken. So here we have taken the step up transformer. In the step up transformer, the number of turns in the secondary side are greater, so naturally E2 will be greater. Actually E2 is not E2, induced EMF is equal to minus N d phi by dt. It is equal to minus N d phi by dt. So the induced EMF is depending upon the number of turns, and it is depending upon the differentiation of the flux, and the flux is given by phi m sine omega t. We are taking the flux to be phi is equals to phi m sine omega t. Okay, so d phi by dt will give us phi m omega cos omega t. Okay, and so my E will be equal to minus N d phi by dt. We will be placing this. If we want to write cos omega t in terms of sine omega t, if we want to write cos omega t in terms of sine omega t, then we will be writing as N d phi by dt. So phi m omega sine omega t minus pi by 2. So that's why the phase difference between the EMF and flux is 90 degrees. So we have seen that the phase difference between the EMF and flux is always 90 degrees. That's why we will be drawing our EMF with a phase difference of 90 degrees. So let us start drawing our EMF. So let us say this is E1, let us say this is E2. Okay, now this E2, because of this E2, the current I2 started flowing through the secondary winding, because the secondary winding was closed through the load, and the load we have taken is the inductive load. So let us draw our current. This is I2. So the load is inductive, so the current will lag the voltage V2 by some angle. Okay, so the V2 will be coming over here somewhere. Okay, so V2 will be coming over here. Okay, so it is, let us say the phase angle between the I2 and V2 be phi 2. Okay, let us say the phase angle be phi 2. They are having a phase difference of phi 2 over here. Now I2, here is E1. If I have to draw minus E1, then it will be on this side. This side I will be having minus E1. Okay, because minus sign, this is E1 magnitude, here we are taking positive, so that side it is negative, it will be minus E1. It is similar as we see in the coordinate axis in our mathematics coordinate axis. Positive sides we are taking upwards, and negative signs we are taking negative magnitude of all the magnitude of y axis we are taking downwards. But here if we are taking here positive, so this will be minus E1 over here. Okay, so now I2 dash will be here. I2 dash will be here, just opposite of I2. Why? Because I2 dash was the load component of the primary current, and it was the current which was nullifying the effect, weakening effect of the flux which was created by I2, So it will be just drawn opposite to I2. I2 dash will be just drawn opposite to I2. Okay, so now now we need to draw our load component, no load currents, okay, and the components of the no load also. So let us say I naught having two components. We already know the core loss component and the magnetizing component. So magnetizing component will be drawn over here, I mu, and here will be the core loss component, and the resultant will be somewhere here, okay, resultant will be somewhere here. So it will be I naught. So it will be I naught. Okay, so it will be I naught. Now I1, we have already seen I1 is the summation of I naught and I2 dash. So taking the summation of these two, we will be getting I1. We will be getting here our I1. Okay, so this will be our I1, which is the primary current, of the transformer, So we have drawn till now. Now we have to draw our voltage across the resistance R1, voltage across the resistance X1. X1 is the reactance, voltage across the reactance, and minus E1 already we have drawn, and the voltage source V1 will be the vector sum of all these three. V1 will be the vector sum of I1 R1, I1 X1 and E1. Okay. So minus E1 we are already having over here. Now we need to draw the I1 R1. Now you can see over here the resistance quantity is there. So wherever the resistance is there, the voltage across the resistance will be in phase with the current. So I1 R1 will be in phase with I1. I1 R1 will be in phase with I1. So here is I1. So we need to draw a line parallel to this. This is representing my minus E1 over here. So we will be drawing a line parallel to I1. So when we will draw parallel to I1, we will be getting over here I1 R1. We will be getting over here I1 R1. Okay. So this is representing our I1. That means the voltage across the resistance R1. Okay, the voltage across the resistance R1. Now the next quantity is the voltage across the reactance X1. So the voltage, we have drawn this. Now the next quantity is the voltage across the reactance X1. So whenever the reactance come, it is considered to be the inductive case. So in the inductive case, the current always lags and the voltage always leads by 90 degrees. Okay. So here we will be drawing our I1 X1 to be leading, because I1 X1 will be the voltage across the reactance. So the voltage across the reactance will be leading the current. The current is this, I1 will be leading the current by 90 degrees. Let us say by 90 degrees. Okay. So this is I1, I1 X1. Okay. So we have got minus E1. We have got the drop I1 R1. We have also got the drop I1 X1. So taking the vector sum of all these three, we will be getting my V1 according to the KVL equation at the primary. So the upper part is representing the primary side. So we will be getting our V1 over here. So now let us see where does it meet over here. It will be meeting somewhere upwards. So I'll be writing this load to be here. Okay, so this will be my V1. So this will be my V1. So V1 is the sum of E1 I1 R1 and J I1 X1. That means V1 is the vector sum of the voltage across the resistance, which is I1 R1, the voltage across the reactance, which is I1 X1, and minus E1. So this will be my V1. So we have completed drawing for the primary side. Now let us start with the secondary side. So at the secondary side we have got all V2 we have got. Now we can clearly see over here that E2 minus I2 R2 minus J I2 X2 minus V2 is equal to 0. That means E2 is the vector sum of the voltage across the secondary resistance, the voltage across the secondary reactance, and the terminal voltage V2. So V2 is already over here. So let us start drawing our I2 X2. So I2 X2 will be in phase with I2. Okay, I2 X2 is the voltage across the resistance. I2 X2 is the voltage across the resistance whenever the resistance part comes. So the voltages and currents are always in phase with each other. So drawing parallel. So we need to draw parallel to this. So this will be R2. This will be I2 R2. Okay, so now we need to draw I2 X2, which is the voltage across the reactance, secondary reactance X2. So that will be leading the voltage, by 90 degrees. Okay, so let us draw it. That is leading the voltage by 90 degrees. So this is J I2 X2. So this is my current. You can draw further also. So you can see this current and you can see this. So this is leading. This is leading the current by 90 degrees. And when you will proceed it further, this will join somewhere here. This E2 will be joining here. Which is the vector sum. Okay, so this is the vector sum. I'm not having a ruler over here. If you will be taking the ruler, you will be getting the exact straight lines you will be getting. Okay, you can draw by ruler, getting the straight lines. Okay, so this will be E2. Okay, so this will be E2. Actually, this should come straight. Okay, so this will be my E2. E2 will be the vector sum of the voltage across the resistance, voltage across the reactance, and the terminal voltage V2, which we have already seen in the KVL equation at the secondary side. Okay, so in this manner we need to draw the phasor diagram. So this was for the lagging load. Okay, this was for the lagging load. In the next videos, we will be drawing for the capacitive load, which is the leading load. Okay, in the capacitive load, the current will be leading the voltage by some phase angle phi. Okay, so we have left here the phase angle to be represented. So I1 and V1 will be having some phase phi 1, and I0 and V1 will be having the phase of phi naught. Okay, and we have already seen the phase angle between the V2 and I2 is phi 2. So they will be always having some phase difference. So this is the phasor diagram and it will be drawn in this manner only. Okay, so thank you. So please subscribe my channel, please share my videos, and if you have any doubt you can ask me in the comment section. Thank you.